So let's discuss complex metal ions. First of all, the definition of the complex ion is a metal ion that is bonded by dative covalent bonds to ligands. And the definition of ligands is an ion or molecule with at least one lone pair of electrons, which forms a dative covalent bond with a metal ion. A dative bond, which we'll revisit in the next chapter, means that both of the electrons in a covalent bond come from only one atom, and that's compared to a normal covalent bond where each of the electrons in that covalent bond comes from each of the atom of that bond. So looking at, for example, the copper 2 plus ion, when it's dissolved in water, the water molecule will act as a ligand because there are lone pairs of electrons on the oxygen atom. So one of the lone pairs of electrons of oxygen will be used to form a dative covalent bond with the empty orbitals of the copper ion. So water is a really common ligand, but there are actually many other ligands which you can find in table 15 of your data booklet. Now, the ligands are not randomly placed around the central metal ion. Rather, they occupy specific positions. These positions include tetrahedral, octahedral, and square planar, but within the IB syllabus, only octahedral is required. You can learn more about the octahedral structure in Vesper theory, which will be covered in the next chapter. Another skill that you have to know about complex metal ions is figuring out the charge of the metal given the formula of the complex metal ion. So if we take a look at this complex ion here, we have copper, which is covalently bonded to 6 water molecules, and the 6 water molecules here act as ligands, whereas the entire molecule here is the complex metal ion. And the 2 plus charge at the top right hand corner refers to the overall charge of the entire ion, including any charges of ligands. Now, in this specific case, water is a neutral ligand, which means that the 2 plus charge must have come from copper. So the charge of copper would be copper 2 plus. Now let's look at the next example, where the chloride ion acts as a ligand. Referring to the spectrochemical series, the chloride ion ligand has a charge of -1. So the total charge of the ligands would be -1 times 4, which is -4. And to find the charge of the metal ion, we just take the overall charge of the entire complex ion minus the charge on the ligands, in this case giving us 2 plus. Now let's try a more complex example where we are combining complex metal ions with ionic bonds. In this case, the complex metal ion in the square brackets is ionically bonded to a bromide ion. So the 6 ligands, the hydroxide ion and the 4 water molecules, will arrange themselves in an octahedral shape around the central iron ion with an unknown overall charge, and that would be ionically bonded to a bromide ion, which has a charge of -1 since it is a halogen. So this means that the overall charge of the entire complex metal ion must be +1. Then we just have to figure out the total charge of the ligands. So we have -1 from the hydroxide ion and 0 from water, giving us a total charge of 2 minus. And again, to find the charge of the metal ion, we take the entire charge of the complex ion minus the charge on the ligands, giving us a charge of +3. One really common IB question is about the color of transition metal ions. But before we discuss that, we have to understand why objects are colored in the first place. The reason is that light is actually not just white light, but rather is composed of all the colors of the rainbow, Roy G. Biff. So objects will absorb certain wavelengths of light, and the opposite or complementary color is reflected. The complementary color would be the exact opposite color on the color wheel, which is found in number 17 in your data booklet. Now take note of the word reflected, because reflected does not mean produced. To produce light means to be luminescent, which means that the object would be very visible at night. So if we take the example of a solution of copper sulfate, which you may know to be blue colored, it actually absorbs orange light. So referring to the color wheel, the complementary color of orange is blue, which is why the solution appears blue. So the real question here is, why is orange light absorbed? And that leads us to what's called the crystal field theory. When ligands are near the electrons of a transition metal ion, the d orbitals become split into two different energy levels. Two orbitals will have a higher energy and three orbitals will have lower energy. So the energy difference between these two different orbitals corresponds to a very particular wavelength of visible light in the electromagnetic spectrum. So an electron that is in the lower three orbitals can absorb that amount of energy and be promoted to the higher energy level. And this transition is known as d-d transition. Now take note that for this transition to occur, the d orbitals must be partially filled. And this means that there must be the presence of unpaired electrons. And that's why compounds like scandium or zinc are colorless, since they do not have unpaired electrons. A very common IB question would ask about why a particular compound is colored, and here is the model answer. The presence of ligands causes the partially filled d orbitals to split. Electrons absorb energy to undergo d-d transition and be promoted to a higher energy level. The energy absorbed corresponds to a wavelength of light in the visible region of the electromagnetic spectrum, and the complementary color is seen. So one exam skill is that if you know the color of the solution, it might be better to mention those exact colors. So going back to the example of the copper sulfate solution, since we know that the solution is blue, it will be absorbing orange light. So you can say that the energy corresponds to a wavelength of orange light, and the complementary color, blue, is seen. Now, obviously, not all solutions are blue, so there are different factors that affect the extent of the splitting of the d orbitals. And these are the three factors you must know about. Number one, the oxidation state of the metal ion. Number two, the nature or the identity of the ligand. And lastly, the identity of the metal ion itself. So these three factors will cause different energy difference between the split d orbitals, resulting in a different amount of energy being absorbed and thus a different colors observed. So we'll focus on the second factor, the identity of a ligand, which is a common question. And we'll be looking at the example of a nickel complex ion to understand this in greater detail. So let's compare these two complex ions, the hexa-aqua nickel ion and the hexaamine nickel ion, the first being green and the second being blue. And the difference here is the ligand being used. In the first, the ligand is water, and in the second complex ion, the ligand is switched to be ammonia. Focusing on the blue hexaamine nickel ion, blue light is observed, and referring to the color wheel, that means that the complementary color, orange light, is being absorbed. And for the green hexa-aqua nickel ion, green light is observed, so referring to the color wheel, red light is absorbed. So based on the color wheel, we can see that the wavelength of red light is larger than the wavelength of orange light. And translating that in terms of energy, since we know that wavelength is inversely proportional to energy, that means that the energy of red light is less than the energy of orange light. Since ammonia is higher in the spectrochemical series than water, it will cause a larger energy difference. That means that the complex ion with the ammonia ligand has absorbed more energy, and the way you can answer this in exams is that ammonia is higher in the spectrochemical series and causes a greater splitting of d orbitals. Thus, orange light, which has a higher energy, is absorbed and blue light is reflected. So in summary, we've covered three really common complex ion questions. One about the charge of the complex metal ion, one about the charge of the ion in the complex metal, one about the charge of the metal ion within the complex ion itself. Secondly, a more general question about why compounds are colored. And the last question being why there may be a color change when different ligands are used. I hope you found this video useful, and I hope to see you in the next video.